Will NASA's Sunbeam Drive, before long, be taking us to far-off star systems? Due to the tremendous distances that exist in space, the dream of interstellar travel appeared as an unfillable wish for quite a while. Yet, now specialists have fostered a progressive concept that should finally make the jump to far-off worlds a reality. And while the double star Alpha Centauri, which is just 4.34 light-years away, appears to be inaccessible with our current means, the new drive technology could get a test to it in only 40 years, a considerable challenge. A simple approach. At first glance, the foundation for the new Sunbeam Drive seems quite basic. As we all know, gas stations in space are hard to come by. But imagine a scenario where we gave a rocket a part that supplies it with the necessary drive energy from the outside during its journey. Well, that's exactly what the new NASA concept visualizes. The spacecraft will not carry its fuel at all. Instead, it will be supported by an external stage that provides the energy supply via a particle beam. Why this specific type of drive could accomplish the definitive leap forward in the field of interstellar travel becomes clear when we consider the staggering velocity increases that are possible with this strategy. Recently, the Parker Solar Probe became the fastest man-made object ever when it moved toward the Sun at a marvelous speed of 692,000 kilometers per hour, a without a doubt great feat. However, it pales into irrelevance when we recall that the speed of light is estimated to be around 1.08 billion kilometers per hour, and that with Sunbeam, it's possible to accelerate a test to 10% of this general maximum speed. All in all, the spacecraft could race through space at a steady 100 million kilometers per hour. But how could that even be possible? Well, the answer to this question is called relativistic electron beams. The electrons accelerated to nearly the speed of light produce sufficient power to drive even a 1,000 kilograms probe across interstellar distances. And when this approach is understood, the Alpha Centauri star system, 4.34 light-years away, is no longer a massive number of travel years away, but just 40 years. This is especially fascinating from an exploration perspective since Alpha Centauri, along with the star Proxima Centauri, which is nearest to the Sun, forms a very triple system that might even harbor a habitable planet, Proxima b. How interstellar travel could become a reality right away. 4.34 light-years may not seem like much, but to get a sense of the immense distances in the universe, it's worth looking at the following example. As is well known, no human-made objects have ever gone as far into space as the two Voyager probes. Expressed in numbers, this actually means that since their launch in 1977, Voyager 1 and 2 have put an incredible 2,481 and 2,074 billion kilometers between them and the Sun, and that's not even a single light day. And just to be clear, despite their old age, the old-timers are by no means chugging through space at a relaxed speed. They are going at around 61,000 kilometers per hour. But then, compared to 100 million kilometers per hour, Voyager's speed seems more like a painfully slow pace. But how does the Sunbeam technology actually work in detail? Well, the center of the drive system is the so-called solar sail, a fixed stage that is placed close to the Sun. It floats in place using light pressure and solar magnetic fields while firing the high-energy electron beam at the probe, protected by a large solar shield. When the focused electron beam hits the probe, it transfers energy, thus continuously accelerating the spacecraft without relying on its own fuel. The longer the beam acts on the probe, the greater the speed increase. But shouldn't the electrons eventually scatter into the infinity of space? Fortunately, they don't. While electrons normally repel each other, they exhibit an amazing behavior when accelerated to relativistic speeds, or, in other words, speeds approaching the speed of light. More specifically, this is a phenomenon known to scientists as the pressure effect, which relies on what is known as time dilation. In very simplified terms, this phenomenon states that moving clocks run increasingly slower. Applied to Sunbeam technology, it means that approaching the speed of light prevents the electrons from drifting apart, and the beam remains steady and focused over vast distances. The benefits over breakthrough projects like Starshot and others. The dream of interstellar travel is not new. In fact, the idea of accelerating a spacecraft to high speeds using an external beam is certainly not new. Starshot, for instance, was launched in 2016 with the idea of investment of galactic greats like Stephen Pedling and Freeman Dyson. The Advancement Starshot Research Project is likewise founded on a rocket that accepts its jolt of energy from outside. Yet, while Sunbeam, as already referenced, should sling a 1,000-kilogram shuttle to interstellar universes, Advancement Starshot depends on a more specific concept. This idea imagines a couple of G-weighty tests the size of a CPU, equipped with a light sail and controlled by a laser. However, this would require not only one, but a colossal array of strong lasers that join to form a 100 gigawatts beam and focus on the miniature test sail a good ways off of 20 million kilometers. The Sunbeam approach sounds considerably more enticing. After all, it would eventually enable us to send a fully fledged research test to the Alpha Centauri system and check, at close range, whether Proxima b does indeed fulfill its standing as a potential world for life. Although the exoplanet probably always turns the same side toward its red dwarf and is consequently divided into a cold night side and a hot day side, there could be a thin, strange place between these two extreme zones that harbors liquid water. Furthermore, if, and this is still a big if, given all the unanswered boundaries, life has already bloomed on Proxima b and this is identified by an interstellar shuttle, this could be the most significant galactic sensation in history. So, what are NASA specialists waiting for? Well, with no guarantees, so often the case, there are still a few obstacles to overcome. While the Sunbeam idea sounds equally simple and promising on paper, the actual execution still holds some demanding challenges. The obstacles to acknowledgement, specifically the issue of energy supply, should be mentioned here. For the relativistic electron pillar to accelerate the test at all, it must obviously first be produced. But that's not all. In fact, all things considered, the high-energy pillar should then also be exactly lined up with the test over vast distances. Even the smallest deviation would make the beam miss the shuttle, carrying the mission to a premature end. Moreover, the pillar requires increasingly more energy to remain viable over increasing distances. Since the solar state is to be positioned near the Sun, as mentioned, it would require materials that can withstand the extreme heat and radiation of our mother star. Luckily, and this is the intriguing part, the accomplishments of the past have shown that the many foundations of progressive impetus technology already exist. Simply check the Large Hadron Collider at CERN, which can produce radiations with a higher energy than is even required for Sunbeam. Simultaneously, the beam direction systems of modern particle accelerators can also pave the way for precise focusing in space. And if we recall the current speed record holder, the Parker Solar Probe, we realize that there are already space probes whose materials can withstand the rendezvous with the Sun. Strong with regard to the question of how to actually generate energy, the specialists have a complex plan up their sleeves. In particular, thermoelectric generators that convert the enormous heat close to the Sun into power. The small but even more critical limit here, however, is that so far, there is essentially no technology that would allow astronomical solar power plants to be realized. So, it will take time before the corresponding technology is developed. And the same applies to the general Sunbeam concept itself. So far, it only exists on paper, and even most hopeful estimates believe at least an additional 20 years will pass before the first Sunbeam model is launched. Notwithstanding the technical execution, however, there is also a completely different question to be resolved. Who will fund the project? The development of a totally new drive technology is likely to cost several $billion, and it's unlikely, without a doubt, that NASA will shoulder these huge costs alone. A more reasonable approach would be for several space agencies to combine efforts, and ideally, bring major, financially strong private investors on board as well. As we can see, a little patience is still required before Sunbeam can be realized. However, it's by no means impossible that we will still witness the launch of the first interstellar exploration probe later on. After all, who knows what breakthroughs will be made in other fields from here on out that will help the Sunbeam Drive. Humanity has already demonstrated time and again what rapid technological advancements it is capable of. After all, when the world's first powered airplane took to the air on December 17, 1903, it took less than 70 years before Neil Armstrong became the first human to step onto the moon's surface. Now, you're welcome to tap on the subscribe button, press approval, and click subscribe to never miss another video from us in the future. We'll see you soon.